As a software developer in 2026, my biggest frustration is waiting around for AI to generate the code or the business that I prompted for. I want it all, and I want it now, and for that, we need faster models. But simply hoping that NVIDIA will ship an even faster GPU might not be the safest bet. The problem is fundamental to how traditional large language models work today. No matter how many GPUs you throw at them, they are ultimately bottlenecked by their sequential nature, generating one token at a time. However, there is a new paradigm that by design doesn't have this limitation: diffusion LLMs. They generate an entire response draft at once and refine it progressively, taking full advantage of the GPU capacity. For instance, Mercury Coder is a diffusion LLM created by Inception that is 5 times faster than similarly sized auto-regressive models like Claude Haiku or Gemini Flash.
We expect the gap to grow even bigger in the sense that we are just getting started with diffusion language models. It's a very new technology and approach, and I think we're still far from even a local optimum.
This is Stefano Ermon, the Stanford professor who helped pioneer diffusion models and is now leading Inception, the company that's making them commercially available. This is a paid collaboration, but the content is strictly technical. In previous videos, we discussed the general paradigm of diffusion LLMs, as well as how they're implemented using the transformer architecture. Here, we'll cover the major open source breakthroughs that make diffusion LLMs so fast: self-distillation, approximate KV caching, block diffusion, and much more. Traditional LLMs produce text responses sequentially, one token at a time, until the special end-of-sequence token is generated. At each step, they re-ingest their own output, which makes them auto-regressive. This sequential dependency puts a lower bound on inference latency, which is linear in the number of output tokens. Diffusion LLMs remove this constraint. Instead of generating one token at a time, they produce an entire response draft at once. They start with complete gibberish and gradually clean it up into a coherent response. This process, which is called denoising or sampling, is executed for a fixed number of steps. So diffusion LLMs bring down inference time complexity from linear in the number of output tokens to a constant. But the speed-up promise only materializes if two things are true. The number of refinement steps has to be low, and each diffusion step has to cost roughly the same as a single autoregressive pass. So we'll start with the first challenge.
One that is really critical is to be able to refine the sentence using a small number of diffusion steps. If you need a lot of diffusion steps, then there is no benefit compared to an autoregressive model. So there is kind of like a statistical problem that you need to be able to train these neural networks to be very efficient at reducing noise and doing the right kinds of modifications to the tokens.
Early diffusion LLMs struggled with this. For instance, consider the original LADA, the first open source diffusion model to scale up to 8 billion parameters and enable head-to-head comparisons with mature autoregressive models like Qwen 2.58b. LADA required up to 1,000 diffusion steps, which largely erased the benefits of parallelism and left it only marginally faster. To address this issue, there's been research on two separate fronts: adjusting training techniques and improving inference algorithms. The ability to decouple these two aspects is quite unique to diffusion models.
In the context of traditional autoregressive LLMs, there is really no freedom. Training and inference are very tightly coupled, and so you train the model to predict the next token, and at inference time, more or less, you kind of like just predict one token at a time. And maybe you can play around a little bit with different kinds of sampling scheme for that single token, top K, top P, greedy, temperature scaling, but roughly that's fixed. In the context of a diffusion language model, there is many more axes that you can explore. There is different kinds of noise processes. You can mask, you can change the value of a token, which correspond to then different kinds of inference algorithms, because then during the denoising, you're going to apply different kinds of edits, different kind of modifications to your text.
We'll first look at the training techniques that aim to keep the number of refinement steps low. To train a diffusion model, we first produce training data through a process called forward diffusion. This takes a clean text and gradually corrupts tokens until it turns into gibberish. These intermediate steps provide a fine-grained training signal. They break down a complex problem into smaller steps, making learning more feasible. But during inference, when the reverse diffusion process mirrors training, a long path translates to many refinement steps and therefore slow inference. And yes, we could shorten the paths, but then learning would become more difficult. Ideally, we'd want long training paths and short inference ones. One promising way to get the best of both worlds is knowledge distillation. Distillation is an older training technique that can be applied to any kind of deep learning models, including auto-regressive and diffusion LLMs. It normally involves two models: an accurate but expensive teacher that shared this knowledge with a smaller but faster student. For diffusion models in particular, it's very common to do self-distillation. A single model is pre-trained on diffusion paths with a reasonably large size n. Once pre-trained, the weights are duplicated. One copy is frozen and will act as the teacher. The other copy acts as the student. It will be fine-tuned to produce shorter paths, say n/2. The teacher paths provide a supervision signal, and the student learns to align every state with every second state in the teacher path. The end result is a model that is now twice as fast and just as good. And we don't need to stop here. We can repeat the distillation process. Duplicate the student, freeze one copy, and fine-tune the other to shrink the paths yet again. Distillation is a post-training technique. It basically fine-tunes an existing diffusion model. But there's ongoing exploration on how to adapt the pre-training process as well, so that lowering the refinement steps is not just an afterthought. One direction is curriculum learning. So under normal circumstances, at each training step, we randomly pick a state or a noise level and teach the model to find its way back to clean data from there. In other words, all task difficulty levels are uniformly spread across the training process. The philosophy behind curriculum learning is to ease the model into it. Train it on easier tasks first with reasonably clean data. And as the training progresses, so does the difficulty level, a bit like a school curriculum. It turns out this makes the model more robust and efficient, able to achieve more in a single step, and that indirectly leads to fewer refinement steps. Distillation and curriculum learning are only two of the many training techniques currently being explored. The research hasn't settled yet on one canonical solution. Which brings us to inference techniques.
There is many different kinds of inference time algorithms that you can use once you have a pre-trained model that provide different kinds of trade-offs between the compute cost and the quality of the results. So just like in traditional image, let's say, diffusion models, there is many kinds of sampling algorithms like DDIM or DDPM or DPM. So there's something similar in the context of diffusion language models.
Diffusion LLMs come in multiple flavors, which I've covered in this previous video. Here, we're going to focus on masked diffusion models like GLADA, which are currently the dominating paradigm. Given a fixed context window, the prompt is concatenated with a response that starts off fully masked. At each denoising step, the model predicts a full response and then remasks a subset of the recently uncovered tokens. On the next iteration, the model uncovers the leftover masks. But this time, the prediction is slightly better since the tokens that survived in the response provide extra structure. The sampler is the inference time algorithm that decides at each step how many tokens to commit and which ones to uncover. A smart sampler can drastically reduce the number of refinement steps because operating on the right tokens at the right time will require fewer corrections in the future. The simplest sampling algorithm selects the tokens to be remasked at random. While naive, its advantage is that it matches the corruption process the model was trained on. But it's not optimal. In this partial response, remasking Beijing is clearly the right move, and it would be silly to leave it up to chance. Instead, LLaDA makes remasking decisions based on confidence scores. Each predicted token comes with an underlying probability distribution over the entire vocabulary. Sharp distributions signal high model confidence, and flat distributions are good candidates for remasking. But even with confidence scores, speed comes at the expense of quality. Consider this partial response where Madrid is named twice. This is not just a rare edge case, it's actually symptomatic of a structural weakness in mask diffusion LLMs. It happened because these two tokens were predicted in parallel without being aware of each other. When uncovering the first mask, the diffusion model made a prediction based on the partially masked sequence. From this perspective, Madrid was a reasonable guess. But the same applies to the second mask. The redundancy only becomes visible at a global level after the two masks are revealed simultaneously. Such inconsistencies get amplified as we decrease the number of refinement steps and implicitly increase how many tokens are decoded in parallel. Confidence scores can't fix this problem. They tell you how sure the model is about each token in isolation, but not whether the sentence makes sense as a whole. So the next obvious move is to add some kind of global signal, something that looks at the draft more holistically to identify inconsistencies and guide token remasking. A reasonable way to do this is guided diffusion, proposed by FlashDLM, a lightweight auto-regressive model that supervises the unmasking process. Given an intermediate draft proposed by the diffusion model, the supervisor makes next word predictions strictly for the recently unmasked positions. The tokens in the draft are then compared against the supervisor predictions. In our case, for the second mask, the supervisor assigns near zero probability to Madrid, which is already in its left context. Since this is very inconsistent with the sharp distribution around Madrid generated by the diffusion model, this token is remasked. At first, guided diffusion might seem counterproductive for latency. We're reintroducing an auto-regressive model, so how can we possibly beat an auto-regressive baseline? The reason is the supervisor isn't a fully fledged generator, but rather a verifier. Because the diffusion model provides a full draft upfront, the ARM can process the entire sequence in a single forward pass and make predictions for the masked positions simultaneously. For instance, Lisbon can be predicted straight away based on this prefix from the draft, and so can Rome based on this other readily available prefix. The auto-regressive supervisor adds minimal overhead. In fact, FlashDLM was 12 times faster than LADA. So far, we addressed the first challenge, keeping the number of refinement steps low. The second challenge is making each individual diffusion step fast. Okay, so say we selected a good sampling algorithm, and now we need to implement it. What are the challenges there? I know you built a custom inference engine. What exactly is custom about it?
Perhaps the easiest way to understand this is that even if you have a traditional autoregressive LLM, if you want to serve it in production, you would probably want to use something like vLLM or SGLang or TensorRT, one of these serving engines that have been built to support continuous batching, caching. There is all kinds of optimizations. So we had to build something similar to support serving diffusion LLMs, which you can't actually run in any of these existing serving engines.
There's been a lot of work optimizing inference for auto-regressive models like KV caching and so on. How many of these tricks translate to diffusion models?
Some of them translate, some of them unfortunately don't, and some of them there are new ones that only apply to diffusion language models and don't necessarily apply to autoregressive models. The architectures that we use are not that different from the traditional autoregressive models. So our models are still largely transformer based. So a lot of the kernels that people have developed to accelerate attention-like computations can still largely be reused. But then, as you mentioned, KV-Cache is much more tricky to use in the context of a diffusion language model because there is not really necessarily a context that stays fixed throughout the computation.
To understand the utility of caching in autoregressive models, let's look at a world without it. You know the drill. We feed the prompt, followed by the special beginning of sequence marker. Internally, the LLM produces contextual embedding X for each input position. Then it produces an embedding for the next token based on everything to its left. This is causal attention. On the next iteration, the predicted token is appended to the input. Now, a naive implementation with no caching would discard the internal state between iterations. So all the input embeddings would have to be recomputed from scratch. So it's clear that a cache would save a lot of duplicated work. Once input embeddings are produced, they are reused across steps. And the cache grows as more tokens are predicted. Now, you might have heard of the more specific name KV-Cache. In practice, instead of storing a single copy of the token embeddings, we store two linear transformations called keys and values. These are the model activations specific to the transformer architecture. KV caching is feasible because of the causal attention. Since tokens only depend on their left context, future predictions don't alter their embeddings, so they're stable across iterations. But that is not the case for diffusion models. Here's a typical input where the response is fully masked. The LLM computes embeddings for the entire context window. Let's assume tokens 3 and 5 are selected to be unmasked into who and there. The refined response becomes the input to the next diffusion step. Now, what happens to the internal state? Naively, we might be tempted to only recompute x3 and x5. They were originally based on the mask token, and now they're outdated. But they're not the only ones that change. Let's look at the first token. Because of the bidirectional attention in a diffusion model, it depends on everything, including the now outdated tokens, so x0 is invalidated as well. So the virus basically spreads to the entire context window. KV caching, as implemented for autoregressive models, is simply not possible for diffusion models. And that's a big setback, since KV caching can speed up inference on autoregressive models by anywhere between 3 to 30 times. However, this doesn't mean diffusion inference has no redundancies to be optimized. They're just not as structurally obvious. While all internal token embeddings do get updated at each denoising step, not all updates have the same magnitude and impact. Consider the prompt portion. While its embeddings do depend on the ever-changing response, its fundamental semantics remain the same. Empirically, studies have shown that the prompt embeddings change very little across consecutive denoising steps. That's why some papers choose to cache them right from the start. I'm calling this cache approximate because the values are only an approximation of the fresh ones we're avoiding to recompute. Some papers, like dLLM-Cache, refresh the cache at regular intervals, say 100 steps, to mitigate the staleness. Researchers also noticed patterns in how the response tokens evolve. For instance, unmasking a token will significantly change its representation. That's why these similarities are low. But their embeddings will stabilize in subsequent steps. Here's what happens after another denoising step where we unmask token 4. The newly decoded token changes a lot since it's no longer a mask. But in the meantime, who and there stabilize compared to the previous step. This is an empirical observation made by multiple studies. One of them is dKV-Cache, where D stands for delayed, as in caching with one-step delay. Now, prompt caching and delayed response caching are ultimately still approximate. However, there is a compromise that enables precise KV caching. The trick is to bring back auto-regression. Given a long context window, we could split it into equally sized blocks. Within a single block, tokens are generated with diffusion. But blocks themselves are generated sequentially from left to right. This hybrid method is called block diffusion or semi-auto-regression. This enables a mixed attention pattern. A particular token within the current block attends causally to all the tokens in previous blocks and bidirectionally to the other tokens in its own block. Causal attention means left blocks are not affected anymore by future updates to the response. Once a block is finalized, the activations in its last denoising step can be cached and reused by future blocks. This is no longer heuristic or approximation like the methods we saw before, it's exact KV caching. Beyond speeding up inference through caching, block diffusion comes with another major advantage: variable length generation. Once the end of sequence is produced, sampling can stop early without filling in the entire context window. Block diffusion is halfway between pure diffusion and auto-regressive LLMs. We see this compromise in most state-of-the-art diffusion research, including seed diffusion and the LADA model family. Are you thinking of diffusion as a replacement for autoregressive models, or do you see them as complementary technologies?
We think of them as a replacement for sure. I see a future where diffusion models will become the leading paradigm, not just for image and video generation, but also for discrete object like text and code. I think they're fundamentally better in terms of the way they scale at inference time. And we're getting to a point where the only thing that matters is really how efficiently you can serve these models at test time, at inference time. And so I'm very optimistic about the future of diffusion language models.
If you're interested in trying out diffusion LLMs, there are multiple ways to get your hands dirty. Hugging Face is a great way to find open source models. You can look for tags like dLLM or LADA and find more than 100 models. If you're looking for a commercial API, Inception offers multiple endpoints for their Mercury models. You can get chat completions that are compatible with the OpenAI API, as well as specialized endpoints that are particularly well served by diffusion models. For instance, fill in the middle, or FIM, is particularly good for code autocomplete. In a future video, we'll see why diffusion LLMs knock this task out of the park compared to autoregressive ones. And if you're interested in digging deeper into diffusion models, you can find my full reading list on Patreon for free. Thanks for watching, and I'll see you next time.